Alrighty, we good, guys? So hopefully we'll be done halfway through this lecture today, and when we come back after the break, we'll finish this lecture. So angular kinetics of human movement. So what are the kinetics parameters that you can think of? Linear ones. Mass, right? Forces, that's linear. Impulse, remember we multiplied force multiplied by the time, that's impulse. Remember we did the torque, correct? And the torque is force multiplied by the distance. And then we have momentum. Remember momentum? We said linear momentum. It's mass multiplied by the velocity, correct? So those are the linear ones. Now we would like to talk about the angular ones because that's what we use in biomechanics. So I would like to look at identify angular analogues of mass, force, momentum, and impulses, right? And what are they? What do we call them, and how to calculate them? And then we'll do a lot of examples. I think we have 4 examples in this lecture, and we'll solve them together just to make sure that we are applying these quantities on the human movement. And we're going to look at the Newton's law. How many laws? Newton's, we have 3 laws: law of inertia, law of reaction, and the law of acceleration. Now we will have, those are linear, so we'll have angular law of inertia, angular law of reaction, angular law of acceleration. We'd like to correlate those and see what they are and how to solve problems with it. And quantitative problems relating the factors that cause or modify angular motion. So I would like to close the circle. We started with kinematics, now kinetics, and we'll relate linear to the angular. And that's the difference between this class and the statics and dynamics class. Make sense? What to do? All right, so let's start. Quickly, what is the moment of inertia? Now, in the linear kinetics, it is mass. In angular kinetics, we don't use masses. We use moment of inertia because things are rotating around the axis of rotation, right? So we need to find something that can give us an idea about analogous of the mass, which is the moment of inertia. So the moment of inertia, if you recall from the statics, you calculated the area moment of inertia. Do you remember this term? The area moment of inertia, you were taking areas and then multiplying that area with the distance from the axis of rotation square. That's called the area moment of inertia. You have the drawings, you had something like this, and we gave you an area, and we said, okay, this is the differential unit, and use the differentiation and get the area moment of inertia by the integrations. Now, the moment of inertia, without saying it's the area moment of inertia, that is what we care about in dynamics. In angular movement. And instead of doing area moment of inertia, replace the area with mass. So you multiply the mass with the distance from the axis of rotation square. That is our moment of inertia. Now, this is really an important quantity, and there's a lot of research opportunities for that in imaging. Samantha, we'll talk about that. So I'm trying to look at the micro CT scans of bone and find the moment of inertia for bone that is diabetic and bone that's non-diabetic. Nobody has ever calculated this before. So that's a cool way of looking into the moment of inertia of the bone distribution. Okay, so the moment of inertia. It's the inertial property for rotating bodies representing resistance to angular acceleration. That's the key thing. We are resisting acceleration. Does it make sense? That is the key for the moment of inertia. Remember, moment of inertia is resistance to move if it's linear. If it's angular, resistance to angular acceleration. Now, based on both, we have mass and the distance that mass distributed from the axis. Now, let me tell you something. See our bone, when we say that it is anisotropic, non-homogeneous, what does that mean? Equally. Yes. So if I'm looking at the calcium, right, and I'm seeing that it's not distributed equally, I can find different values of the moment of inertia for it, correct? And the more homogeneous actually distribution or non-homogeneous, we can assess it using the moment of inertia, using CT scan or an X-ray. So are we good with the moment of inertia? So it's mass now, you multiplied by the distance from the axis of rotation square. And this is an example. So if you look at this, the moment of inertia is the sum. So the sum of the product of each particle mass, m, and the radius of rotation, r, for that particle square. So let's say if I'm saying that this is a bat, right? And I have this mass here, and that's m1, and then I have m2 here, and I have an m3 here. So if I'm distributing each mass inside it, And if I have, this is the axis of rotation, and that's another mass here, I can find the moment of inertia by summing, take each mass multiplied by the distance. So this is d1, d2, and d3, square the distance, add all of them together, that's the moment of inertia of the entire object. And that's something I would like, for example, to assess for the knee or for the lower extremity of the bone. Does it make sense how we look at that? Okay, now an example, a simplified example. So you have two bats, right? And you have a mass placed on the bat. Which one do you think is harder to swing? This one on top or this one here? This is going to be harder because your distance here is larger, right? So D1 is larger than D2, and when you square that D, it's even larger, correct? So it's just like exponential. It's a very big value. So it's harder to swing this bat compared to that one because of the distribution of the mass. So it is resisting angular acceleration more, right? Correct? So although both bats have the same mass, bat A is harder to swing than bat B because the weight ring on it is positions further away from the axis. And we're going to call the moment of inertia I, right? I. Some people call it L. I like to call it I. I don't like the L. So the moment of inertia is the summation of all the masses multiplied by the distance squares. Are we good? Now, look what I did here. I concentrated the entire mass in one point, location, right? In 1D. So that's not real, correct? This is because you have also mass here and mass there. But I did the assumption that all the mass is concentrated in one location. Remember the center of gravity? I considered. So if you have an object and you said, I would like to concentrate all the mass in one location, that distance between the center of rotation and that point is called the radius of gyration, the gyration radius. It's just like you are assuming or simplifying the whole thing as it's in one location. So that's the radius of gyration. So what do we call this? So the radius of gyration, it's the distance from the axis of rotation to a point where the body mass could be concentrated. It's an assumption, right? I'm assuming that it's concentrated there without altering its rotational characteristics. And when we do this, when the moment of inertia for a body known mass has been assessed, the value can be characterized using the formula I equals m, which is the mass of the body, k squared. K is the radius of gyration. K is the distance known as the radius of gyration. Remember? Does it make sense? So it's just an assumption or simplification that all the masses are concentrated there to find the moment of inertia. Are we good, guys, with this? Any questions? Yeah. Yes. And they're going to solve a problem related to that. So, and here's the thing. You have something called local center of gravity, and then you have a global center of gravity. So the global center of gravity is total body. But for my arm, this upper extremity, it has, a center of gravity. And even if I break it down, each one of them have its own center of gravity. So in order to do the whole thing, you need to add all of them together. And we're going to talk about that for the moment of inertia, right? It's very important. Any other questions, guys? We're good? All right. So let me show you something, an application in biomechanics. So in biomechanics, let's say someone is running, sprinting, correct? So you will have, we are rotating around the hip. So let's say we are rotating around the hip, right? Now here's the thing. The femur or the thigh has its center of mass. Do I agree with that? So I can assume that this is here is the center of mass of the thigh itself. Make sense? And then I'm saying, well, this is the center of mass for the shank. And this is the center of mass of the foot. We are good? So I have three different center of masses. And I said, well, to simplify, I'm going to put the concentration of mass in that location. Now, there is a distance between the axis of rotation, which is the hip, and each one of them is K1, K2, and K3. Make sense? Now, if I would like to find the moment of inertia of the entire system, should equal to the summation of mass 1 multiplied by K1 squared, correct? So let me move that. Do you agree? Plus mass 2 multiplied by K2 squared. Make sense? Plus M3 multiplied by K3 squared. Does that make sense for us? How we're going to do this? It's the mass multiplied by the distance squared. Now, here's the thing. The larger the moment of inertia, the larger the resistance to rotation. Correct? Now, which one do you think it's easier to rotate? When you have the leg extended or when it's flexed? Which one would be easier to rotate? You have larger distances when you extend it. And you square it again. So you need to reduce the distance in order to reduce the moment of inertia. Then you can rotate it. So people, athletes who are actually know how to use physics and engineering, what they do when they sprint, they always put their leg as, they flex it as much as possible. Extreme flexion. This way you are not feeling tired and you are rotating quickly. You're doing the acceleration. So people who are sprinting and they don't do extreme flexion, actually they're losing. They're not the one. Look at the world, champions. That's what they do when they sprint. Does it make sense? Because they want to reduce the moment of inertia. The moment of inertia, slows angular acceleration. Does it make sense? We'll go with that. So pay attention to that and that's because the radius of gyration, when you have it extended, Alyssa, the radius is large. So the moment of inertia will be large because k is long. You square it. So let's say this is 0.3 meters, that's 0.4 meters, and that's 0.3 meters. Here, no, you have 0.3 meters is going to be the same, but then you'll probably have here 0.7 and probably 1 meter. And when you square it, that's a large moment of inertia, which means that you are resisting acceleration. Large radius of gyration. Yep. Are we good? Any questions? Okay, then another thing. So the moment of inertia is the thing that represents analogous to masses, and it depends on the distance between the axis of rotation and where the mass is concentrated, right? Now, here's another thing. This is another example. So let's say I'm flexing and extending around the elbow. Now, the mass can be concentrated at this point, right? So you can concentrate your mass here at this point. That's K. That's the distance, the radius of gyration. Now, if you increase or decrease that distance, the tendency to angular acceleration will be harder, right? Now, imagine if you are having a dumbbell here, a weight. What's going to happen to K? It's going to move even further, right? So that's longer. So this, with the dumbbell, you resist acceleration even more because the distance now is larger, and the mass is bigger as well. Does it make sense? We're good with that? Right. Now, so our body rotated multi-axis. So I can do flexion and extension around the elbow, but I also can do this, right? Right. Now here, your axis of the mass can be concentrated here at this point, and that's your K. So you can rotate this quicker than doing this because distance is smaller, right? So the axis of rotation decides actually, how much also the K is, the radius of gyration. Now, keep in mind, moment of inertia resists angular acceleration. If you want to rotate, that's not good, an important value. We need this as small as possible. We good? Now, another example, during sprinting, that's what I was talking about. Extreme flexion at the knee reduces the moment of inertia of the swinging leg, increasing that, which leads to increased acceleration, angular acceleration. So the subject will be faster actually. And try it. And the other thing is that, which is cool, is that if you didn't change the speed, you're not going to feel tired quickly because you are using the moment of inertia to accelerate rather than you having your muscle do the work. Another biomechanics example, there is something called the ratio of muscle strength. So how do we measure strength? Newton, right? It's force, correct? The muscle strength, if you divide a muscle strength by the segmental moment of inertia, this value, this ratio, is very important actually in performance development. So the ratio of muscle strength, that is the ability to produce torque. What is the definition of torque? Which is force multiplied by the distance, right? That's torque, which is moment. Force multiplied by the distance. So the ability to produce torque to the segment moment of inertia that is resistant to rotate around the joint is important performance capability in gymnastics events. And people actually try to assess this. We can calculate these using kinesia. I can get the forces through the velocities, and then I get the torque divided by the moment of inertia with the distribution and the gyration. And do you remember the book that we shared with you with all the measurements of the body? We have the gyration, the radius of gyration, so you can use that. Does it make sense? So it's really an important moment of inertia is very important. Now, here's another representation with numbers. So the principal moment of inertia of the human body is different in different positions, affect different axes. So let's say I'm standing here. What axis is this? Frontal axis, right? And let's say I'm rotating in the frontal plane around the frontal axis. How is that? Right? So I'm swinging in this plane and flipping, right, in this plane. Now, because the masses are distributed away from the center of rotation, the moment of inertia will be large. So you are rotating like this, right? And that's 12 to 15, correct? So this is called anterior posterior rotation, right? Moment of inertia. And that is 12. Now, if I'm rotating around, what axis is this? Sagittal axis, right? That's sagittal axis. That's not the sagittal plane. That's the axis. And I'm rotating around that forward, flipping forward, right? Like this. I still get 10 to 13. So medial lateral rotation. Now, if I tuck myself in, what is happening? My masses are going, so the distance is smaller, correct? Between the mass and the axis of rotation. Your moment of inertia will be very small. And that's what you see when people when they do diving and they tuck to themselves, see how quickly they move the rotation, because the resistance to rotate is not there anymore. So the further the mass away from the body, the larger the moment of inertia, which means that the slower the object, the person, the subject. Make sense? Right? Now, the same thing, when I rotate, this is the longitudinal axis. If I'm rotating around the longitudinal axis in the sagittal plane, right, that's called longitudinal rotation. And see, the masses, this is my axis. The masses are not far away from that axis. So the moment of inertia is small. So I'm doing it like this one. But that's 1 to 1.2. If I extended my hands, what should happen to the moment of inertia? The mass is going away from the axis. So the distance is larger. And the moment should be larger. Let me show you a demonstration, which is a fun one. I was showing it all. And I want you to try it yourself. Remember, the moment of inertia will stop the acceleration, which means you're going to be moving slowly. So if I have these dumbbells here, and I did this, and I did that, see how quickly I'm moving? Because the mass is away now from there, so the acceleration will be. I didn't do anything, I just was doing like this. That's quickly, see how the acceleration is slower? And that's actually, if you have, athletes actually benefit from this, especially, so, when they rotate, they jump, and they go in, keep spinning, and they move their hands in different ways, and they change the axes. It's all moment, all, because the friction is very small. Make sense? I feel terrified. I have to go stop that thing. Okay, are we good? Make sense? Alrighty, so the principal axis decides how much the distance is. The principal axis is the axis we rotate around. It decides how much the masses are away from that distance and that. Now, what is the unit of the moment of inertia? It's mass multiplied by the distance square. So it's kilogram multiplied by meter square. We good with that? The moment of inertia with it. Now, the area moment of inertia should be an exam question. What's the unit? Area moment of inertia. It's meter to the power 4. Because you have area, meter by meter, that's meter square. Multiplied by another meter square, that's meter to the power 4. The area moment of inertia is the area multiplied by the distance square. So the area is meter multiplied by meter, and then meter square. So it's meter to the power 4. Now the moment of inertia, which is the mass, that's kilogram meter square. To calculate that. Yeah, it's a fun thing. I keep, confusing students with that. Do you remember the area moment of inertia? We need to do something about it. We need to have one more class before you go to your junior year that is more engineering somehow in the sophomore. I need to teach it. I need to teach you. You should be with me. I need to see you earlier more. That's my point for them. Okay, so we go to this. Now before we do an example. We did moment of inertia, correct? It's 1. That's mass multiplied by distance square. We good. Now there's something called the momentum. You remember the momentum? What do we remember the momentum in linear momentum? It was mass multiplied by velocity. That's momentum, right? Not moment or torque, it's momentum. Mass multiplied by velocity. Now, mass, we agreed that we're not going to use masses in angular anymore. We're going to use moment of inertia. And velocities, we're not going to use linear velocity, we need to use angular velocities. So instead of mass multiplied by v, like momentum, we're going to do I multiplied by w. So anywhere you're using masses in angular measurements, ditch the mass and put the moment of inertia. Mass multiplied by the distance square. That's how we do it. And then you do the w. So it's a quantity of angular motion possessed by a body and measured as the product of the moment of inertia. Remember, angular, we deal with masses. Moment of inertia. I multiplied by the angular velocity, which is w. So, and the term for it is h, or the symbol. And it's I, that's moment of inertia multiplied by w. And I, we agreed on, it's the mass multiplied by the k square, which is the gyration, radius of gyration. So your h is mk squared multiplied by w. And so what I'm trying to do is I'm going to present to you the angular quantities, bless you, that we're going to be working on for our biomechanics. So as mass or angular velocity increase, the angular momentum increase proportionally. Does it make sense? Higher moment of inertia, higher momentum, which means that also higher velocity, higher momentum, right? It's linear. A factor that influences angular moment is the distribution of mass with respect to the axis of gyration. If the masses are distributed away from the axis, what do you have? Larger moment of inertia, correct? The I will be larger, which means h will be larger, the momentum will be larger. Angular momentum is proportional to the square of the radius of the gyration. That's another thing. It's just I'm looking at the value. Now let's solve an example together. Let me give you pieces of paper. Okay, guys. So the question is, we have a rotating 10 kilogram body for which k is 0.2. What is k? The radius of gyration, right? So I'm assuming that all the mass is concentrated away from the axis of rotation that much distance. And then the w, the angular velocity, is 3 rad per second. Pay attention to the units. And I would like to see what is the effect of the body. What is the effect on the body angular momentum? Momentum is I multiplied by w, correct? If the mass doubles, if the radius of gyration doubles, and if the angular velocity doubles. So let's take 3 minutes and see if you can tell what's the effect on the momentum if you change these values, double these values, or if you did double. Yes. So let's say, we're talking about the momentum. So the momentum is h, right? And h equals I, the mass, which is the moment of inertia in angular, multiplied by w. And I equals the mass itself, k square, multiplied by w, right? This is angular momentum. So the angular momentum is h. I is the moment of inertia. W is the angular velocity. Yes, that's the first thing. And then see if you double, what's going to happen with the value. That's absolutely correct. You have the numbers, right? And then I wanted to tell me, is it going to double, half, quadruple, triple? What is going to happen to that value? So you divide it by the original. Yes, always your measurements, always, if it's angular, rads and radians. Do not calculate with degrees. Yeah, do not convert to degrees or revolutions. If it's in degrees or revolution, you need to convert to radians. Guys, that's very important. Does it make sense? All your angular quantities should be radians. Do not calculate with degrees or revolutions. So the units of the momentum, so you have kilograms, then meter square, and then you have rad per second. That's W. Now the what is the unit of linear momentum? It's kilogram meters per second, right? Right, because that's mass multiplied by velocity. So your mass is staying like this. Meter square. No, it will say like this. That's the unit. Kilogram meter square rad per second. Yeah, that's a good question. Oh, kilogram meters per second. Oh, rads will go. The radians. No, radians will go because that's the distance now with the other distance. So the radians, as long as they're rad, they will go. Yep, you're right. Yes, meter square. And the reason why we took the radians away because of the meter square. You're right. Kilogram meter square. And see the difference between it and the linear is that meter is square, and that's an indication of the moment of inertia. Yeah, you're right. Yes, kilogram meter square per second. Okay, so what happened when we double the mass? Doubles the momentum. What happened when we double the radius of gyration? So quadruple. It's quadruple. Now, what does that mean? So that let me tell you, this is a really cool thing. It means that the momentum is a geometrical property. So if you change the radius of gyration, the impact is way bigger than changing the masses. Does that make sense? So it doesn't matter how big a subject is, if he or she can actually move their body structure, configuration in such a way to increase that distance, they will have larger momentum. Does it make sense? So what I will say is that the angular momentum is much more sensitive to the radius of gyration than the mass. So what happened with angular velocity? If you double the velocity, it just doubled, just like the mass. So the one that is more sensitive to is the radius of gyration because of the square, actually, because of squaring the distance. Yeah, do you confirm? Double, quadruple, double. And that's something called sensitivity analysis. If we would like to see which parameter is actually more affecting the parameter that we would like to. So if you do the calculations, you'll get this. Do we have 1.2 kilogram meters per square per second? 2.4, that doubles, quadruple, double. Now, larger momentum means the acceleration, we're trying to slow the acceleration, but if I'm hitting a soccer ball with a larger momentum, what do you think is going? Is the ball is going to move further, right? So the larger the momentum, the larger that you are transferring the energy to that thing that you are hitting. And that's an example here. The angular momentum of a swinging leg. So this is the swinging leg, right? It's two things actually. You have something local and something called global. So you have your lower leg rotating around the knee. Do you agree? And that's called WS. But I'm still having the whole leg is rotating around the hip, correct? So I have two things. The angular momentum is the summation of the local and the global parameters. So what happens is that you have IS, the moment of inertia of the swing, multiplied by the velocity of the lower leg, plus the mass of the entire, entire leg with the radius from the hip multiplied by the swinging of the entire leg. So you have two things because they're like a multi-segment pendulum system, right? So you have your leg moving, but also you have the other lower leg is moving as well. In order to solve this problem, we need to add the two together. Does that make sense, guys? That's a very important concept. When we look at the body is a multi-segment coupled pendulum system. You will have global and local segments to deal with, to work with. Is this good? Example? Especially the angular momentum, you need to add them together. Cool. Now, what is the principle of, now we talked about the angular momentum, which is I multiplied by W, right? Now, same thing, we had the principle of the linear momentum, there's conservation of momentum. We have also conservation of the angular momentum. So when the gravity is the only acting external force, angular momentum is conserved, okay? And again, what is the angular momentum? I multiplied by W. Do you agree? I is the moment of inertia, W is the speed, the rotation, right? Let me show you something. Let's go back to this example. So let me show you something. So if I said to you that, well, I have IW, that's H, right? This value should always be conserved, the H. If I'm moving faster, what should happen to the I? Should go slower. If I'm moving slower, what should happen to I? Should go up. So that's the balance. One of them will go up and the other will go down as long to keep that thing conserved. Does it make sense? We're good with that? And when you see when I moved my hands away, the velocity was slower, but the moment of inertia was higher, correct? Because distance was further away. And that is the principle of conservation of angular momentum. When gravity is the only acting force, angular momentum is conserved. The total angular momentum of a given system remains constant in the absence of external torques. Now, remember, because it's angular, I'm not talking about torques. Forces, I'm talking about torques, right? If you are dealing with angular movement, do not say torque. Don't say force, replace it with torque, and do not say mass, replace it with inertia, moment of inertia. Does it make sense? We're good, guys? Okay, now let me show you what does that mean in another example. So here, if you have this player, the change in see at this moment here, this point, because the athlete is extended her length, her body, the distance is far away, correct? So I is high, but the velocity is low. As she tuck in, what happened is that the velocity will get larger and the moment of inertia will get smaller. But always H should be constant. Does it make sense? And when she, like here, the velocity is higher and I is very small because she's rotating quickly around the axis. And when she dives in, she increases the moment of inertia but reduces the velocity, so slow the no rotation, and then H always conserved. So when angular momentum is conserved, changes in the body configuration produce trade-off between the moment of inertia, and the angular velocity. With the tuck position, produce a greater angular velocities. Does it make sense? Make sense, guys? With this, H should always be constant if there's no external torques acting on it. Alrighty. Example. So let's spend 2 more minutes. Let's say 3 minutes. So if you have a 60 kilogram diver, is positioned so that the radius of gyration is 0.5. So that's K. So I'm assuming that the mass is concentrated 0.5 meters from the center of rotation. He leaves the board with an angular velocity of 4 rads. What is the diver angular velocity when he assumes a tuck position, altering the radius of gyration to 0.25? Remember, h is always h equals IW, and I equals mass k square. Don't forget the square multiplied by W. H should always be constant, different in the two positions. So this principle is really important when you're designing robotics, especially big machinery, because that momentum could be really large with bigger machines. But for us, it's robotics. Okay, so how much is the momentum, the angular momentum for the position 1? 60. That is kilogram meter square. Don't forget the dot per second, right? We good? Now, this 60 is going to be, it's conserved, right? So 60 should equal now position 2, the data from position 2, which is the mass is the same, correct? So that's 60 kilograms multiplied by k squared. Now k is 0.25, right? If I'm giving it to you in centimeters, or you always need to make sure that it is in meters. 0.25 square, and you multiply it by W, which we don't know, right? Now, divide everything by 60 multiplied by 0.25 square, right? So 60.25 square. That goes with this. How much is W? 1/6. So W 1/6 kilogram. Don't forget the dot. Yes, there you go. Now we're talking. Rad. We good? Make sense? Awesome. And this is the solution of it. 60 checks, 16 checks. We good? Okay, so we solved that. Now, the angular momentum. So that's, again, the more you know about this principle, the more actually you can do athletically. So, and if you look at the airborne execution of a spike in volleyball, you see when someone is hitting that ball as hard as they possible want to, they actually do flexion for the knees. What they do is actually they're reducing the moment of inertia. And what are they doing? They're increasing their angular velocities. Does that make sense? Because you want to pass that velocity to the ball. So you reduce the moment of inertia and increase velocity. Momentum will be conserved, and then you can hit it with a very, very large angular velocity. Does that make sense? How we do that? Right. So rotation of the lower extremity offset the forceful swing arm so that the total body angular momentum is conserved, and then the velocity is transferred to the ball itself. Now, another example for divers, again, if you are aware of these principles, you can actually, a skillful human performer can rotate 180 degrees with zero angular momentum just by changing the location of the center of the mass, the radius of gyration. Does that make sense? So you can just play with that, identify, make sure that you know where the masses should be and how you tack yourself around the axis of rotation. You can increase the velocity really quickly, and you can have 180 degrees. Remember, it's always moment of inertia and angular velocity. Your momentum should always be conserved. You can do this, and then you should be fine with that. Okay, so that's this. Now, what produces change in angular momentum? So we said angular momentum is conserved. So what can change this? The angular momentum. So the only thing that can change the angular momentum is actually the product of the torque and the time intervals. And that's called angular impulse. Remember impulse? What was the linear impulse? Yes, force multiplied by time, that's linear impulse. Now, angular impulse, we said don't use force, we use torque, correct? So you multiply the torque by the time, and that's your angular impulse. And that's the only thing that can create a change in the momentum. Now, here's the thing. If I'm swinging my hand, right? And then I stopped. So I was swinging, I have acceleration. Then I stopped it. What do you think the thing that stopped my hand? That's angular impulse. But what is the thing that can create an angular impulse? Muscles, right? So our muscles are the ones who can counter the angular movement with angular impulses. So torque multiplied by time equals the change in the momentum. And the change of momentum is I multiplied, it is moment of inertia multiplied by W2 after, which is minus the IW1 before. Are we good with this? So let's solve an example. That's called angular impulse. Are we good with angular impulse? Torque multiplied by time. So angular impulse, this is an example. What average amount of force must be applied by the elbow flexors inserting at an average perpendicular distance of 1.5 centimeters from the axis of rotation at the elbow over a period of 0.3 seconds to stop a motion of a 3.5 kilogram arm swinging with the angular velocity 5 rad per second, where k equals 20 centimeters. Right? So here's the thing. I have two conditions. I have something swinging and it stops. It's swinging, so that's angular momentum, correct? And then I would like to find force. Now, we remember we talked about torque. So torque multiplied by, here's the formula. So the torque multiplied by time equals the change in momentum, correct? Now, what is torque? Torque is force multiplied by distance, multiplied by time equals h after minus h before. Let's fill the parameters, the values. See what do you have and try to fill this. Remember, this is something was swinging and it stops. So that's a immediately angular momentum conservation problem. So it should be torque multiplied by time equals the change in the momentum. And see from the values that you have here, see which one you can fill. Remember, 20 centimeters need to be converted to meters. Rad per second can stay rad per second. Kilogram can stays. 0.3 seconds can stays. 1.3 centimeters need to be changed to meters. Do not have anything that centimeter stays in centimeters. And you need to find force, F, correct? Needed to stop the swinging. Remember, what is H, by the way? I W2 minus I W1. And I, what is I? I is mass K square W2 minus MK square W1. Right? That's M, right? That's the mass. Yeah. And then you have FDT. I think you'll have all of them now. So when I say it stops, what's W2? 0. Yeah. Angular impulse. So the torque, you can convert it as an M as a moment, right? Oh, for the angle,
like the variable.
But it's a good one. I think there is one. Oh, we'll see. Okay, do you have value, guys? Minus 155 confirmed. Yep, that's absolutely true. So if you do this with the filling the values, TT, that's the torque is the force multiplied by the distance time. I have the distance, which is how much away from the swinging, right? That's the force. And the time is there. W2 is 0 because it stops swinging. And then you fill the values that you have and you get minus. Now here's the thing, make sure that it is negative because that force is stopping the movement. Should be in the opposite direction of that movement. Do not forget the negative. Does that make sense? How we look at that? We good? Okay, I would like to stop here, and when we come back we will continue with the other examples and how to do that thing together. Does that make sense? We good? Any questions? Alrighty, please take a picture. I will create a Dropbox for this one so that we have week 14. So let's